Alright class, let's go ahead and solve a problem based on the topic 8.1 and 8.2 Exergy chapter. So I'm going to use the McGraw-Hill book Thermodynamics Engineering Approach 8th edition. So I'm going to solve the problem 8.12 exercise problem 8.12. Basically this problem is saying that there is a electric power need in a community, right? So electric power needs of a community are to be met by windmills with 40-meter diameter rotors. So this is one information, wind turbine, and the diameter is 40 meter. And then the steady airflow velocity of that area, steady airflow velocity is equals to airflow velocity is 6 meter per second of that area. Now determine the minimum number of the wind turbine to generate total of 1500 kilowatt power, right? So basically let's solve this problem. Basically it is asking us that how many power plant or how many wind turbine we need to install in that area to generate 1500 kilowatt power. So basically we have the velocity. Let's first think we need to calculate the kinetic energy, right? Kinetic energy due to the air velocity, Ke, which is equals to v square divided by 2, equals to 36 over 2, which is 18. Okay, I think no, here is the important thing. V square divided by 2, which is equals to 6 meter per second, right? Square divided by 2. However, we have to convert this kinetic energy in kilojoule per kg. So if we would like to convert this kinetic energy in kilojoule per kg, then we have to use this formula. 1 over 1000 meter square second square 1 kilojoule per kg, right? So we have to add this term, now multiply this term. So now the kinetic energy will be 36 by 2 divided by 1000, so which is 0.018 kilojoule per kg, right? So for 1 kg of airflow it will generate 0.018 kilojoule of energy. So now we got the kinetic energy. We have to determine the mass flow for that particular wind turbine blade. So how much is the mass flow? So mass flow is rho times A times B, right? So we know the density of the air 1.18 times pi d square divided by 4 times velocity. So what is this thing? Basically, if you have a wind turbine like this, right? If you have this wind turbine installed, right, then this air velocity is 6 meter per second. 6 meter per second is coming, and this rotor diameter, right, this is 40 meter, right? So we have to determine how much airflow is coming through this rotor diameter. So that's what this formula, mass flow, right? So let's plug in all those value. Mass flow 1.18 times pi times d square, which is 40 square divided by 4 times velocity is 6. So mass flow will be in terms of kg per second, which is 1.18 times pi times and t, which is equals to 8897 kg per second. So we know the mass flow rate, right? So now how the maximum power can be produced by one single turbine. Maximum power can be produced by a turbine, right? Wind turbine or windmill, whatever you say, is equals to mass flow times kinetic energy, which is 8897 times kinetic energy. We got 0.018, which equals to 160 kilowatt. The total power requirement requirement was actually, let me write it this way. Requirement was 1500, right? 1500 kilowatt. So number of windmill is equals to 1500 divided by 160, which is 9. So we need total 9 turbine. So that's the answer, right? So this is the answer. We need total 9 turbine to generate 1500 kilowatt. So that's the problem for based on the